different based on the Raman shift, but there are some background different. So for example, the one you are using of 700 nanometer, you nearly have no background in your spectrum. But once you are changed that to shorter wavelength, you see some hump start to appear. And those humps sometimes would like block the Raman signal you desire to analyze. So here I would like to let you guys know what are those humps and why they are forming. So based on this result, you can know that. We can just jump into slide 14. So actually this is slide 14, and when you plot, you know this one is based on the absolute wavelength and using different excitation laser. But whenever, and this are the the arrow I plot you guys is somewhere that's close to your excitation laser wavelength. Okay, so this is somewhere the red light scattering occurring. Okay, so all your spectrum are plotting based on this excitation wavelength. Okay, so to further look at this, you can realize there's a background over here, right? So those background would make sure some of the signal is not so obvious. So based on those results, you can know that actually whenever you are analyzing this polystyrene, this kind of polymer, the best way to analyze that is using local wavelength laser. But what are those? What are those background is? That's the fluorescence. Okay, so what are those fluorescence? Photoluminescence. So actually those background is coming from the fluorescence. So as I mentioned previously, those Raman signal are coming from the scattering. Okay, but even though you are observing the scattering, but the electron from your material or from the molecule, it's also having the possibility being excited from one electronic state to other electronic states. Okay, and then when that relaxes back to like another state, the fluorescence would appear. It would pretty similar to the XAS spectrum that we just mentioned. So for the fluorescence, you can think like that would be something pretty similar to what we told previously. You excite the electron from more co-level electron, probably from s orbital to the p orbital, and then after the relaxation back to initial states, some energy, some photoluminescence will occur. And in Raman spectroscopy, the most commonly seen one should be the fluorescence. Okay, so in short for that, we are trying to observing the scattering from your sample. Let me see. So we are trying to observing the scattering light, but those lasers having the strong excitation, it's probably would also excite the electron from the ground state to another electronic state. And when that relaxes back, you will observe some fluorescence in your spectrum. Okay? But one thing you should know is scattering. Scattering, all of this scattering are based on the excitation. Okay? So once you plot them in the Raman shift result, those scattering should be aligned to each other. But the fluorescence is correlated to the electronic state of your material. it's nothing related to your what your excitation is. Okay, so the wavelength for that would be maximum at a specific point. For example, in this kind of case, the fluorescence is maximum around 500 nanometers. So if you want to reduce the fluorescence contribution, you should choose the higher excitation wavelength. Is that clear? So the main takeaway is like, let me write down over here, the Raman scattering would let's talk about the absolute wavelength case, okay? When you change the laser to higher energy, you also shift your Raman scattering. I'm just plot R, okay? But you are not changing the fluorescence wavelength, okay? That's pretty makes sense, right? Because the fluorescence only coming from the electronic states different. You never ever can change that based on the laser you have. But the Raman signal actually is something related to your excitation. So based on this, you can understand why if you check some Raman equipment, most of the time, we will assemble like more than one laser light source on the Raman spectrometer. Because if you have different material, the fluorescence will locate at different wavelengths. So you commonly use different laser to avoid those fluorescence influence. Okay? So now you know why you see this kind of spectrum. Here I would like to share with you is something like more practical data, okay? So in this case, again, we are plotting based on Raman shift. And if you look at the Raman spectroscopy over here, they are using glass microscope slides. So that's kind of a glass slide. So glass slides is commonly used in Raman spectroscopy, but those glass slides actually have a serious fluorescence. Okay, so for example, when you use 500 nanometer one, you can clearly see the Raman peaks. But whenever you use other like 600 and 701, those fluorescence will appear in your spectrum, and especially you can look at the 601 compared to 501. Your Raman scattering nearly disappear because those fluorescence will cover all the data from your Raman scattering. So based on this, you can understand if your, the glass slides would have a significant fluorescence around 600. I did not prepare that over here. So if you plot that for the absolute result, you can know that the fluorescence in that case is different from this case. In this case, the fluorescence is more serious on the low wavelength one, but in that case, the fluorescence is more significant on the high wavelength case. So if your Raman signal is located in the low wavelength, just like this one over here, you cannot use glass slides for analyze that. And lots of biological, some cell. If you observe if you're biological research, and you want to observe some particle or something, vibration in the cell, and the cell commonly having the Raman signal located like a local wavelength, then you cannot use the glass lights for analyze them. The other choice is you should use the quartz, okay, rather than using the glass. Okay, as you can see over here, whenever you use quartz, there is nearly no fluorescence appear in your spectrum. Okay, and you can observe relatively like obvious Raman scattering as compared to whenever you use the glass light. So here is another example to let you guys know how the fluorescence or photoluminescence influence your spectrum. Okay? So another thing you should know is now, again, if we plotting based on the Raman spectrum on the absolute wavelength, and you see those results, you need to have the ability to distinguish which are the Raman peaks, which are the fluorescence. Okay, so now you can see those two are aligned well to each other, but those like spikes are like separate on different wavelength. So based on this spectrum, do you know which one are the fluorescence and which one are the Raman peaks? You know, as I mark here, those two should be the Raman peaks, right? But you should know the reason. And you know, as I mentioned, those are coming from different excitation laser, and the Raman peaks are the scattering from the original light. So whenever you are using different lights for excite your material, here we are talking about the molybdenum disulfide. Okay. If you're plotting based on the wavelength, then you would see the those Raman peaks appear in different wavelength. Okay, and those are the PL signal, the photoluminescence signal, and because they are coming from the energy, the excitation level difference for your material, and they are fluorescence, so they will not ever they cannot change the location even though you are change the laser. Okay, so that's the reason. So if I'm trying to plot, if I'm not giving you the Raman bands over here, and I'm providing you guys this kind of spectrum, and I told you this is Raman spectrum, could you try to distinguish which signal are Raman spectrum and which signal are fluorescence? You need to have the ability to distinguish that. Okay, so that's probably one of the midterm exam question. Okay, and here is another to let you guys get the flavor is the Raman shift one. So in the Raman shift one, as I mentioned, those if they are aligned pretty good to for the Raman shift case, those should be the Raman signal. Okay, so those should be the Raman signal. But the one appear sometimes over here, and whenever you change another excitation, you cannot see that. You are pretty sure those are the fluorescence. Okay, so again, if I'm not providing you guys any like notes on top of that, and I just plotting you, give you guys this is Raman spectrum or this is the Raman spectrum, you should have the ability to distinguish